Okay, I'm going to look at problem 513. This is a little bit different, I think, than what we've seen in the past. And this is a distributed load problem. So we have, the load is distributed in this fashion. If you thought about these as little incremental forces, um, it'd be 900 Newton meters all the way down to get to here, it'd be 600 Newton meters. So as you're going down, the force is reduced. The second part of this is a uniform distribution, so it's 600 newtons per meter. And what we need to do with both of these is come up with a center of mass, okay? So, or a center of gravity is really, if you want to think about it in terms of force, right? So we have this, if we took this whole part here, what we would say is that um, you'd have a certain force and it would be acting. We want to make an equivalent force acting at a specific position. Okay, so that's what we're going to look at doing that. And what we want to do is determine the reactions. So you can see that this is a roller support over here. So this will go freely back and forth in the x direction. But there's a reaction here pushing back up a normal force in the y direction. So we're going to have a reaction here straight up in the y direction. Okay. And this is a pin support. This one resists motion in the x direction and also in the y direction. So we're going to have a reaction in the x direction and a reaction in the y direction. So overall for this problem, we have three reactions that we need to determine. Okay, so the first part of this problem, thinking about this, we need to come up with an equivalent force at a position for these, okay? And one way to go about solving this is to think about like this being 600 Newton meters straight across, all the way across like this. And then coming up with a force, 600 newtons per meter. And if you think about it, if you go straight across here and forget about this, the triangular component that's above that, you'd have a uniform distribution and at 600 newtons per meter. So if you wanted to find the center of a uniform distribution, of course, it's just going to be right down the middle, okay, between the two, okay? Um, the other one, if you think about it, you have, just if we drew a line, straight line here, we would have to come up with a form to figure out what the center of mass is this, or center of gravity for this distribution of force. So that'd be the first part. We'll look at that. Okay, so here's my sketch. It's not very straight lines, but that's about the best I can do now. Maybe I get a ruler next time. Okay, so here's our 600 newtons per meter, right? So this is pretty easy. If we wanted to find the center of mass in this, since it's a uniform distribution, we're going to find it straight here, dead center, right in the middle. And what's the magnitude of this? Well, it's just going to be 600 times 6 meters. Okay, so the whole distance. So it's the area, essentially, underneath this curve. That gives you the number of the total force. So it's 6 meters times 600 newtons per meter, which is just 3,600 newtons, and it's acting straight in the center here. Okay, so that's the first one. All right, the second one, now we're going to take it and just look at it as 300 Newton meters, because it's actually 900, right? So I'm just going to add 300 over here. And it goes from 300 newtons per meter all the way down to 0, okay? Well, one of the things we haven't really covered, we haven't covered yet, and it's actually a topic that's covered later in the text, but I just wanted to give you an idea of how you could calculate the center of mass. Now, this is going to work for any triangular, and there's only triangles or uniform distributions, triangular distributions of our forces acting on an object. So, so the way you calculate it is this. If you're looking for that position, okay, for the center of mass, what you would do is you would do the integral of x times delta dx. Sorry, not dx, dA. Okay, so you're integrating over the area times x, essentially. You divide that by the area. Okay, so this is just the integral for the area. Well, I could go and do the integral and determine what it is, but guess what? It's just a triangle. So a triangle, the area under the curve here is just going to be 1/2 times its magnitude times 3 meters times its length, right? So it's just half. So performing this denominator calculation, the area is just going to be 450 newtons, all right? Now what we need to do is we need to think about the function dA, okay? So dA is essentially just an incremental area. So it's a height times a width. So this is like the width of a little tiny element, right? And this is the height at a certain point. This is the function of the height, all right? Well, this is just a straight line, right, for the height, or the y, if you want to say. So what do we have? It starts off at 300, and then at 3, when x is equal to 3, it becomes 0. So here's the formula for it. Where does it actually come from? Well, we could think about it as this. This is a slope-intercept form. We could just say y is equal to, mx plus some constant, which is our intercept. So we look over here, our y value, where our intercept, so when x is equal to 0, it's equal to 300. Okay, so that's what this is. The other thing is this is our slope and times x, which is just our slope times x essentially. And our slope is minus 100. So it starts off at 300 and it goes down to 0 at this point. So the whole equation becomes that. So it's just slope times x. Well, the slope on this is minus 100. Okay, so here's the actual equation for our line. It's just 300 minus 100x. Okay? All right. Okay, so if I perform that integration, here's my x, and this is all my dA here. Okay, this is dA, little incremental area. And we're going to do it from 0 to 3 meters, right? So we're starting from 0 and going out to 3 meters. Okay, so when I perform the integral, it just becomes 300x squared over 2, which is this term right here. And then the second one, the 100 minus 100x squared, which just becomes minus 100x cubed over 3. And then we evaluate it at 0 and 3 meters, the limits. At the limits, we come up with 1350, which is this from this term, and minus 900 from here. Okay. Well, our final step, of course, this just gives us the numerator. So the numerator is 450, and the denominator, what we previously found was the area is also 450. So our position for the center of mass is going to be essentially 1 meter from the initial part. Okay. And the force acting, it's 450 newtons, which was just essentially the denominator from this equation. So what do we have? We have two forces, so we can represent essentially those two distributions of force or distributions of weight as the first one, the 3,600 newtons acting at the center, and the second one, the 450 newtons acting 1 meter from point A. Okay. Okay, I'll go right to the author's solution set and work on it and then just talk about the solution. Because there's really, after you come up with the free body diagram, there's really not much different than what we've already seen. So the parts that I showed you is probably something that's a little different. Okay, so first part is free body diagram from this, okay? So you came up with the triangle, the triangular portion of this, of the distributed weight. That was just going to be the 450, like I said, acting at 1 meter from the left. Okay. The second one is 600 times 6, which is the area of the other one of these uniform distribution. And that one is acting at 3 meters over. Okay. So what we want to do is we can come up with 3 equations. We can come up with summation of the forces in the x direction, summation of the forces in the y direction, and a moment about some point would give us all our unknowns. Okay, So the first one we could do is look at the summation of the forces in the x direction. All right. And when we do that, and it's got to be equal to 0, of course, because this thing's in equilibrium, what we find is Bx is the only one in the x direction. So, of course, that one has to be equal to 0. Okay? The next thing we could do is, now I'll take a look at it and do it the same way the author did. But, of course, you could have done it. You could do the moment about 2 different points, and the author chose to do it a moment about point B and a moment about point A. Okay? You could have done the summation of the forces in the y direction also. That would have also worked. But okay, let's look at it this way. All right, so first thing, starting from moment about point B. And of course, the author just writes it here as plus direction, meaning that it's positive, it's going in a counterclockwise direction. That's for both of these, okay? So first part is moment about point B, which is a good choice because now what we find if we do the moment about point B, we have a force here, and a force here. And we only have one unknown from that, okay? So the first part is we're going to have, from this point, 3 meters and a force of 3,600 newtons. And that's what this is. That's the first one. And it would cause counterclockwise rotation about this point, so it's positive. Okay. The next one is this one, which is just 450 essentially. And the distance from BY is 5. So here's the 5. And here's the 450. Okay? And the last one, and that one, of course, is also positive. The last one is NA, which would cause clockwise rotation about this point. So that one is going to give us a negative. So it's NA times 6. Of course, put everything over on the other side of the equation, divide by 6, and you come up with NA equal to 2.175 kNewtons. Okay? The next part is finding the moment about, and you could choose anything. I mean, you could choose it about A like it did, or like I said, you could say summation of the forces in the y direction. If you did that, you could also, the only thing left would be BY, and you could solve for it. But the author chose to do it about A. Okay, so now doing the moment about A. Well, BX, of course, is 0, and it doesn't add anything to this point anyway, since if you drew the line of action, it would go straight through A. Okay, so now writing this equation, it's going to be, this one causes counterclockwise rotation about A. So BY times the 6 meters, and that's what we have here. And then the other two are, if you think about point A, these two cause clockwise rotation, so these two would be negative. Okay, so it's the 450 times 1 meter, and that's what this is, which is a negative. And then 600 times 3 meters, I'm sorry, 600 times 6, so this is 3,600 times 3 meters equals 0. And then you could solve for BY. And that's pretty much it for this problem. But like I said, you could have done it with another equation. You could have done the summation of forces at Y, which you can always use that to check, check your work if you wanted to. Because what you recognize is that NA, 2.175 kNewtons, and BY, 1.875 kNewtons. And notice that these both are positive, so they're telling us, yes, we drew them in the right direction. So if you added those two together, what you'll find is that, this one plus this one is going to give you the, 450 and the 3,600. So here's 3,600, here's the 450. So 4,050. Okay, and that's what this comes out to be. Okay, and that's good for that one.